is Yuichi Tsuda, who is going to tell us about exploration of C-type asteroid, achievements of Hayabusa2 mission in the Ryugu proximity operation. So I would like now to invite Mr. Tsuda to give this invited talk.
Thank you for the introduction and the good morning, everyone. So can I now share my screen? I cannot find the screen share button on my software.
There is a rectangle with an arrow in the menu below.
Yeah, but
I think it's sorry, no, I have to make you a presenter, but I was just searching for you in the list. So let me give me the time. Yes, now yes, you're the last one. Okay, now sorry. Now you should be able to share your screen. Try again, please.
Okay. Yeah, I could find. Can you all see my screen?
Yes, sure.
Yep.
Okay. So again, good morning, Andy. Thank you for the introduction, and also I would like to appreciate very much to give me the opportunity to present about the Hayabusa2 mission in the Stardust-R event. So the title of my talk is the Exploring C-type Asteroid, the Achievements of Hayabusa2 in the Ryugu Proximity Operation. And my name is Yuichi Tsuda, and I am the project manager of the Hayabusa2 mission in JAXA. So the Hayabusa2 is the second Japanese sample return mission to small bodies, and we launched the Hayabusa2 spacecraft in 2014 to explore the C-type asteroid called Ryugu. And actually now all the exploration has been over, and the spacecraft itself is now on the way back to the Earth to return to the Earth in 3 months from now, in December 2020. So here I listed some of the feature of this mission. It is a round-trip mission enabled by high specific impulse ion engine for continuous trajectory control. And in the proximity of Ryugu, the spacecraft will stay there for about 1.5 years to do the in-situ science, using 4 landers and also the 4 remote science instruments, and there are some other devices to do the in-situ science. And the biggest highlight of this mission is the touching down and sample collection to the surface of the asteroid. For originally we had planned 2 normal touchdown and 1 pinpoint touchdown. So in total 3 touchdown. The spacecraft is capable of doing 3 touchdowns. But in reality, because of the very harsh environment of Ryugu, we decided to do 2 touchdowns only, but both of them are pinpoint touchdowns, so a more difficult one compared to the normal touchdown. So I will show you that later. And another thing the novel thing that we attempted is the artificial crater generation on the surface of the asteroid. So the spacecraft is equipped with a kinetic impact device called Small Carrion Impactor to make the larger than 2-meter class crater on the surface of the asteroid. The objective of that is to investigate the subsurface structure of the asteroid, and if a situation allows, we were to collect the sample of the exposed subsurface material. So this is the overview of the mission scenario. The spacecraft was launched on December 3rd, 2014, and after 3.5 years of the interplanetary cruise, we successfully arrived at the Ryugu on June 27th, 2018. That's 2 years ago already. And there we stayed for about 1.5 year, doing many attempts, interesting attempts like rover deployments and the 2 touchdowns and 1 kinetic impact operation and so on. And the spacecraft already left the Ryugu on November 13, 2019. It's last year. It was last year, and now the spacecraft is on the way back to the Earth to return to the Earth on December 6, 2020. Actually, in European time, I think it's December 5th, 2020. So this is the trajectory design of the Hayabusa2. The left figure shows the forward trip, and the right figure shows the return trip. And the forward trip spends about 3.5 years with the 1 Earth swing by and the very long ion engine and continuous thrust maneuvers. And compared to the forward trip, return trip is very simple. It's a direct flight from the Ryugu to the Earth, taking only about 1 year. And the return trip delta V is 0.3 km per second, which is 1/4 of the forward trip. And this chart focuses on the forward trip trajectory. So first, the spacecraft launched to the Earth synchronous orbit around the Sun, and make the Earth swing by just 1 year after the launch, and then inserted to the Ryugu transfer orbit, moving around the Sun twice, and then arrive at the Ryugu on June 27th, 2018. And this is the final part of the Ryugu arrival, because the Ryugu itself is uncertain in terms of the ephemeris, which has the orbital ephemeris error of about 140 km, 1 sigma. So, but the spacecraft had to arrive at the Ryugu with the ±100 meter accuracy. So the spacecraft has to improve the ephemeris of Ryugu by itself. So for that, we utilize the onboard optical navigation and optical and radiometric hybrid navigation 3 months or 4 months prior to the arrival, and that was successful. And eventually, we could refine the ephemeris of the asteroid to the level of about less than 1 kilometer. So we could improve the ephemeris of the Ryugu and also the spacecraft arrival guidance in parallel. And this is a movie showing the Ryugu navigation camera images obtained from the Hayabusa2. So you can see the growing Ryugu as we approach to the asteroid. And actually, this is the first time we see the shape of the Ryugu, and we are surprised about the shape itself first, because as you now know that the Ryugu shape is the top shape, but before arrival of the Hayabusa2, we didn't expect this kind of shape. The top shape itself is famous for the asteroid community, but we did not expect the top shape for the Ryugu. So that's actually the first surprise for us. And this is the picture of the Ryugu. As you can see, the it's a top shape with the very large crater on the equatorial ridge, and the size is about 1 kilometer, and it's a retrograde orbit. So in this picture, the South Pole is on the top, and the North Pole is on the bottom. And you can see on the South Pole there's a big rock, a white rock. And here in this chart, I'm showing some initial scientific findings of the Ryugu. It's a top shape, and we found that its spectral time is CB, as we expected from the ground-based telescope. And the size is 450 meter radius, and the mass is about 450 million tons, which corresponds to the density of over 1.2. So it's just a little bit heavier than water, which means that the Ryugu is very porous, and is probably a rubble pile asteroid. And its obliquity is 8 degrees, so it's upright but retrograde. And the rotation period is about 7.6 hours. And it's a very dark asteroid. And in fact, if you see this Ryugu in the naked eye, it looks like this. So it's a very, very dark, very black asteroid with a reflectance ratio of about only 2%. And one of the biggest trouble or findings about this Ryugu is the boulder covers all over the surface of the asteroid. So that was a very, very huge headache for us, our operation planning, because we could not find any flat surface to land the spacecraft safely. Okay, so this is the overview of the Hayabusa2 spacecraft itself. It's a very small spacecraft with the mass of only about 609 kilograms, but with the very high performance ion engine, which is capable of accelerating up to 3.2 kilometers per second if you use all the propellant. But actually, we only used half of them to make the round trip to the Ryugu. So another half will be, actually I will show you later, and that will be used for the extended mission. And you can see the sampler horn here, which is to collect the sample from the surface, and the kinetic impact device called SCI, which is also equipped on the bottom of the spacecraft. And here you can see the reentry capsule that is to be deployed right before the reentry to the right before the reentry of the capsule on December 6th this year. So here is a list of the scientific payloads of the Hayabusa2. We have in total 11 scientific payloads, which consists of 4 in situ remote science instruments, and also the sampler horn to collect the sample, and the kinetic impact device, and the separation camera that is to observe the kinetic impact event from the remote distance. And also we have 4 rovers, and one of them are the mascot rover, which was developed by the DLR and CNES, our European partners, and that is actually the biggest landers equipped on this Hayabusa2 spacecraft, and this was also very, very successful. And this is showing you some pictures of the 12 deployables. So the Hayabusa2 is one of the interesting things engineering-wise of the Hayabusa2 spacecraft is we have as many as 12 deployables aboard the spacecraft, and we already deployed most of them on the surface of the Ryugu. For example, the deployable camera was separated as we did the kinetic impact operation in April 5th last year. And mascot lander is here, and the 3 Japanese rovers are here and here. So which were called Minerva-2 1 rovers and Minerva-2 2 rovers. And here you can see the small carrion impactor, which is to do the kinetic impact. And the we also have the target markers. We have 5 target markers to do the precision landing of the mother spacecraft. And we actually used 2 of them for the precision landing themselves, and another 2 for the gravity science. For that, we deployed 2 target markers to the two orbits around the Ryugu, and we still have 1 target marker left aboard the spacecraft. And the spacecraft itself was delivered to the surface of asteroid once in February 22nd and the second time on June 11th. Those are both successful. And the of course, re-entry capsule is still aboard the spacecraft, which is to deploy 3 months later. So this is the basic strategy we took after we arrived at Ryugu, and we spent most of the duration in the asteroid stay in the home position, which is located 20 kilometers above the surface toward the sun direction. So from this direction, we can point our high gain antenna toward the Earth precisely, and also the solar array paddle roughly oriented to the sun. And also the most of the scientific instruments aboard the bottom of the spacecraft oriented toward the asteroid. And sometimes we moved, the spacecraft moved to this direction or this direction to observe the asteroid from the different angles. And also sometimes we attempted the descent operation to observe the Ryugu in higher resolution, and also attempt the touchdown or rover deployments. And because the Earth's distance is about 240 to 360 million kilometers, so it takes about 13 to 20 minutes round trip time, one-way trip time. So we cannot put the spacecraft closer to the Earth with manual commanding. So the spacecraft is equipped with the autonomous feature to make the autonomous guidance and control below 500 meters. So this is the list of the accomplishments we did in the proximity of 1.5 years of the proximity operation. So most of them were successful, but the 2 of them are aborted because the spacecraft automatically detected some dangerous condition and aborted the descent operation. But as you can see, we succeeded in Minerva mascot rovers deployment, and also the touchdown here, kinetic impact operation here, and the second touchdown here, and target marker or rover orbiting operation here. And this is the statistics of the operation summary. The planned low altitude descent was 17, but we have 18. We have some aboard, and also we have some rearrangement of the schedule. So we actually did the 18 low altitude descent, and the design allowed the spacecraft to do the touchdown three times maximum, but we actually did two times. And all of 4 rovers or landers are deployed to the surface, and we also make the artificial crater And we have 5 target markers, but we used 4 of them, and 1 is left, still left. And there was no plan of orbiting objects to orbit around the asteroid, but because we have an extra target marker after completing two touchdowns, so we attempted 3 target marker orbiting around the asteroid. So after arrival, just 1.5 months after the arrival, we actually held the landing site selection meeting, participated by 109 international partners from DLR, CNES, and NASA, and also JAXA and Japanese universities. So, so for that, using 1.5 months after the arrival, we did extensive observation to decide where to land the Hayabusa2 spacecraft and where to land the 3 rovers on the surface, so that those 3 are not interfered with each other and maximize the scientific outcomes. And so this one-day meeting was very, very fruitful, and only in 1 day we could reach the consensus to make the landing of each object to as you see in this slide. So the key to the successful meeting of this meeting is that because we did extensive training prior to this meeting, so we spent 2 years for the landing site selection training with the international community. So everything went very, very smooth, and besides the very harsh environment of Ryugu, we concluded that let's go for touchdown to this site or this site on this site. And the first thing after, based on the landing site selection meeting, was to deploy the lander or rover to the surface. So first, rovers to be those that are deployed from the spacecraft is the Minerva 2-1 rover on September 21st, and then 2 weeks later we deployed the mascot rover from DLR and CNES. And these 3 rovers could autonomously acted on the surface of the asteroid and make many fruitful scientific activities. And here are some examples. You can see that the very high resolution, very close-up image of the Ryugu surface can be seen from these images. And there are several scientific instruments aboard these rovers other than camera. But yeah, let me skip because I have no sufficient time to introduce all of them. So the next thing and the biggest attempt that we want to do is to make the another spacecraft landing, but because the Ryugu is covered by many boulders, homogeneously bumpy all over the globe, so we could not find a safe area. The original design of Hayabusa2 allowed us to have 50-meter landing accuracy only, which means that we have to find 100-meter by 100-meter safe area, flat area, to guarantee the safe landing of the spacecraft. But there's no such place on the surface of asteroid. For example, this is the L08 area. The width of this square is 100 meter by 100 meter. So if the spacecraft aims at the center of this square, but because there's the landing error of about 50 meter, So the spacecraft may hit the very big rock like this. That's not acceptable for the spacecraft. And if we see this area more with a more high resolution, so it's very you can see this very harsh environment without any help. So originally we have made several strategies to find or search out the landing area, but none of them were actually worked for the Ryugu environment. And so we went back to the very primitive but very powerful analysis, counting rocks from the images. So the result is something like this. So we counted all of the rock on the surface of this region, and also measure the size of the rocks. We also measure the length of the shadow so that we could acquire the height of each rocks. And by doing so, we could find some safe area within L08 area, which is all of them are very small, but because no landing is not an option for us, so we are obliged to choose one from this safe region. And for that, we had to refine or improve our landing accuracy to adjust to the Ryugu environment. And actually, I will show you later, but in reality, we try to utilize a target marker to do the precise landing. And we initially tried to put the target marker here on the center of this largest safe region, which is about 20-meter diameter. But in reality, after the operation, we found that the target marker actually dropped here. So we decided not to land to the large region, but actually try to land in a very small region, 6-meter diameter region, because it's it's closer to the target marker. And at that time we got the confidence that we could achieve 3-meter accuracy landing. So this is again the summary of the landing site narrowing down process. So we found that the L08 area is the safest region, although it's not sufficiently safe. And we tried to narrow down where in L08 area is the safest, and finally found this region, which is about 20-meter width flat area, and try to put the target marker on the center of this safe region, like this. So this 10-centimeter ball is called the target marker, which is a reflective ball. And the spacecraft afterward tries to chase that target marker for the precise landing. And the result was that the target marker was actually settled here, which is 15 meters away from the targeted area site. 15 meters is, by the way, it's a very good performance, because we expected from the original design, we expected 50-meter landing accuracy, but we actually dropped the target marker only 15 meters off. But it's not enough for the very harsh environment of Ryugu. But we actually did another things in this target marker drop operation, which is here. So after the dropping the target marker, spacecraft tried to chase that dropping target marker to place that target marker always on the center of the navigation camera. So this is the movie of the navigation camera, and you can see that the bright spot, which is a target marker, is properly placed on the center of the virtual box. And this virtual box corresponds to the 1 meter by 1 meter size. So this means that once the spacecraft automatically find the target marker and successfully trace that, then we could guide the spacecraft with relative to that target marker with plus minus 50 centimeter accuracy. So that was the actually the key to our successful touchdown. And as you can see, the target marker was actually placed here, which is 15 meters away from the original safe zone. So, and we found that it's a little bit far from the target marker. So we decided to find closer place, closer flat and flat place, which was found here, which is only about 6 meter diameter, which means that the spacecraft has to land with a 3 meter accuracy landing. And finally we could rearrange the autonomous landing program and upload that to the onboard software again. And then this is the finally decided sequence. So the spacecraft is to hover at 8.5 meter, tracing the target marker and moving horizontally toward the place right above the landing site, which is 4 meters away from the target marker, and then adjusting the landing altitude, and then free fall from 8.5 meters. And the landing itself is like a touch and go, just a 3-second event. And the projectile is ejected from the root of the sampler horn, and the reflected soil will be collected to the re-entry capsule. And the spacecraft itself ascends immediately after the detection of the landing. And the February 22nd, last year, we attempted the first touchdown. And this is the final moment right before the touchdown. Yes, so you can see many fragments upcoming. That's a reaction of the projectile ejection and also the thruster firing for ascent. Then as we obtain this kind of very beautiful, clear picture of the landing, we could identify where we actually landed, which is only 1 meter away from the targeted point. And also we could identify from which stone or which terrain we could sample, and which is shown here. So so the first landing was very successful. And after that, only 1 month after that, we attempted very new things, which is a kinetic impact operation. So the target point for the kinetic impact is here. And we attempted the kinetic impact on April 5th last year. And before and after the impact operation, we actually did the same operation twice to observe the planned target area for the terrain survey, so that finally we could compare the terrain change before and after the kinetic impact. And the kinetic impact operation itself is like this. So at the 500 meter altitude, the SCI is to be deployed, and this SCI is to detonate. And before that, spacecraft has to escape from the dangerous zone to evacuate from the detonation debris and also the impact ejector. To avoid that, the spacecraft has to escape to the backside of the asteroid. And after the escape of the spacecraft, the SCI detonates, and the impact event itself is to be observed by the remote separation camera that is to stay or left on the dangerous area to observe the kinetic impact event, and before before it is destroyed, this separation camera took all the images and relayed it to the mother spacecraft by the radio wave. So this is the image of the SCI impact operation. So this is the SCI, and this thing will detonate. And before that, spacecraft has to escape to the backside of the asteroid. And SCI is working by timer, so it's like a timer bomb. Yeah, like this. So the 2 kilogram pure copper will be accelerated to up to 2 kilometers per second in only about 1 millisecond to make a kinetic impact. And that was so successful. And this is the terrain change before and after the impact. And we could make a 40-meter diameter crater with the 2.7 meter depth the artificial crater. And the bottom figure shows the image from the DCAM, and this is a separation camera, and you can see that we could observe the event of the kinetic impact, and we could observe the 40-meter height ejector upwarding from the as a reaction of the kinetic impact. And we could from this we could expect that the huge amount of ejector will be put on the around the surface around the artificial crater. And after that, we could we analyzed the how much ejector is accumulated around the SCI crater, and this is a little bit a processed image data with the black region corresponds to a thick ejector accumulation. And you can see that in the northern part of the SCI crater, we could observe the thick ejector. And because the crater itself is very dangerous for landing, we decided to land on the just 20 meters north of the crater center, where we could expect a thick subsurface material. And we attempted the second touchdown 3 months from the kinetic impact on July 11th, 2019. So here's the SCI crater or artificial crater, and 20 kilometers away from there we could find the safe region. Because we already succeeded in 1 meter accuracy landing, there are many landing candidates around the SCI crater with the like 4 to 6 meter width, because 4 to 6 meter is enough for our precision landing. And as we did in the first touchdown, we first dropped the target marker aiming at the C01CB area, and this time we could drop the target marker only 2.6 meters away from the target from the aimed point, which is far better than the first target marker drop. And after that, we attempted the second touchdown on July 11th. So here, this movie is the result of the second touchdown below 8.5 meter activity. and the beautiful landing. So this time again we could evaluate where we could land, and this time even better achievements were obtained, as we have only 60 centimeter error from the target point. So as you can imagine that the spacecraft Earth distance is this time 240 million kilometers. So 240 million kilometers away, 60 centimeter accuracy. That's a very, very satisfactory engineering achievement for us. And this is a little bit emotional picture. You can see the side view when the spacecraft land to the second touchdown point. Here's a touchdown point, and here we could see the target marker, although it's very faint. And 20 meters away, we have a CI crater. So we could obtain this kind of image as well. So here I show some initial scientific outcomes from Ryugu, and all of them are already published in the Science journal. For example, we could find a weak absorption, which is a clue of 2.72 micrometer, which is a clue of the hydraulic minerals or water on the surface of the Ryugu. And also the Professor Sugita make the classification of the surface rocks based on the visual spectrum. And also one of the interesting finding is from that journal, that paper is we could identify 2 parent body candidates of the Ryugu. So Ryugu is not as it was for billion of years. So before the mother Ryugu is originated from the main belt body, and there's 2 candidates for that. One is Oiraria, and one is the one is Oiraria, and the 2 of them are bigger asteroids compared to the Ryugu. And from the spectrum analysis, we found that the one of 2 candidates are the mother asteroid of the Ryugu. And the mascot also achieves some scientific achievements. And from the observation of the mascot camera, it discovered the structure very similar to the carbonate chondrite meteoroids of the Earth, and also the thermal image analysis brought as the large porosity implicated from the TIR image or thermal infrared radiation image. And from the kinetic impact operation, we found that the cohesion strength of the surface of this asteroid is very, very low, which means which could constrain that by combining with the number density of the crater, we could constrain the age of the surface of the Ryugu of about 10 million years. And that's another big scientific achievement of the Hayabusa2. And besides the very serious engineering and the scientific activity, one of the interesting activity, actually this is also a serious one, but the naming the terrain of Ryugu. So because the Ryugu is stands for the Dragon Palace in the Japanese fairy tale, So we named some of the terrain of the Ryugu from after the world fairy tale. Some of them, or many of them, are from the Japanese fairy tale, but some are from the international or world fairy tale, like Colombo Crater, or Sandurian Crater, which is Cinderella, or Bravo Crater, and so on. All of them are, most of them are authorized by IAU, so it's a human official terrain name of Ryugu. And the final thing we attempted on the Ryugu proximity is the target markers and the Minerva-2 rover orbiting operation, which were conducted on September 16th and October 2nd, 2019. So because we have 3 target markers left after the 2 touchdowns, so we decided to use 2 of them for gravity science and for the training, for the rehearsal, for the inserting the Minerva-2 rover to the orbit. So we successfully dropped the target marker, 2 target markers on September 16th at once. And after that, we also deployed the Minerva-2 rover, not directly to the surface of the Ryugu, but via the orbit around the Ryugu, so that we could do some gravity science. And this is one of the resulting pictures from the target marker orbiting. Probably it's very faint, but you may see the moving objects around the surface, which are 2 target markers. One is the moving in the equatorial orbit, and the another is moving in the polar orbit. So we are now assessing this motion from the optical navigation results, and we are now trying to retrieve the higher order gravity coefficients. So eventually, finally, these 7 items are what we achieved in the Ryugu proximity operation from the engineering point of view. Some of them are the mobile exploration rovers on the surface, and the another is related to the successful touchdown, like 60 centimeter accurate landing and multiple landing on the asteroid and subsurface material sampling. And the another one is artificial crater forming and its observation of the impact process and so on. And now many scientific outcomes are being generated, and some of them are published in Science and many other journals. The spacecraft already left the Ryugu on November 13th, and after that we used the ion engine twice to put the spacecraft to the Earth re-entry corridor. And now the spacecraft is around here. We are almost finishing the second and final ion engine burn, and I think that will end in the September 16th, so we are almost done. And after that, we will shift to the terminal re-entry guidance phase to return back to the Earth on December 6th this year. So this is the final sequence of the re-entry guidance, which consists of 6 trajectory correction maneuvers, and out of them, the 5 TCMs are to guide the spacecraft to the re-entry corridor, and the final one is to make the spacecraft divert from the re-entry corridor for the Earth escape orbit. So different from the Hayabusa1 spacecraft, because the spacecraft itself is healthy at this moment, the spacecraft will escape from the Earth's gravity to make to continue to the extended mission. And the reentry capsule flies alone for about 12 hours to enter to the atmosphere to land on the Australian territory. So this is the reentry sequence. So after 12 hours of the flight, the reentry capsule will re-enter to the atmosphere, and at the 10-kilometer altitude, the parachute is to be deployed and to land to the desert, Umer Desert of the Australia.
Just a short note, about 3 minutes left.
Okay. I have only 2 slides left.
Okay, good.
So this is to briefly explain, introduce about the extended mission. Because everything is successful right now, we are now making the extended mission plans. Because the spacecraft still has 50% xenon fuel left, which is to propel, which is to drive the ion engine, and also we have 25% of the chemical fuel left. So using those remaining resources, so we are we have been planning the what we can do for the extended mission, extra mission. And now we narrowed down the scenario to 2. So both of them are very, very long journey. From 10 years from now, around 10 years from now, we will aim at arriving at one of 2 fast rotator asteroids, which is both of them are very, very small, like 30 to 50 meter 50 meter diameter, but 10 minutes rotating, very, very fast rotating asteroid. So for that, we will make another 2 or 3 swing by to the Earth or Venus. And we are now choosing from these 2 scenarios to one based on the engineering feasibility. So I hope we can announce which one we actually choose very soon. Okay, this is the last end of my talk, and I'm very happy to take any questions. Thank you very much.